In this video, we're going to solve the problems in homework 2 on essentials of inventory management. The first two problems are about economic order quantity. Essentially the same problem, two parts. Elsa Frost has to order two types of tires from a distant supplier. So it's the same supplier providing multiple products. And we need to help her figure out what is the optimal ordering quantity for premium tires, the first product, and then for discount tires, the second product. I'm also going to show you where you can find the explanation for this type of problem in the slides. So if you go to the slides and you go to optimal order size, this is also called EOQ, or economic order quantity. You can see from the formula it says EOQ formula, EOQ. Now this formula right here, which is the simple EOQ formula, is not relevant for us because this formula works when you order from one supplier, one product. We still have one supplier, but we have multiple products. We have two products. And when you have multiple products, this formula, the simple one, is not relevant. So we go to the next slide. That's just an example. We go on. Optimal lot size, which is the ordering size, optimal lot size Q, for multiple products with combined shipping / ordering. So this is the formula we are going to use when we either have one supplier supplying multiple products, so that one supplier can obviously ship multiple products together in one shipment, or you have two or three or multiple suppliers in the same town or city, or close enough to each other that you can pick up material from all of them into one truck or one shipment and ship them. So some 3PLs will provide you this service where they can pick up product from multiple suppliers, combine it into one big shipment, and then send it to you. Okay, so that case where your suppliers are close to each other, so you can get one shipment, or you have one supplier, so you get one shipment, but you have multiple products, is this situation right here. Optimal lot size for multiple products with combined shipping. So we're going to have to use this formula. Now remember, the first formula here directly found EOQ quantity Q star by just applying this formula. But in this case, we have to do like a two-step approach. Okay. In the first step, we find N star, which is the optimal number of orders to place in a year. So if you know the optimal number of orders to place for a product, how do I get to the order size? Well, I know my annual demand. So let's say my annual demand is 10,000 and N star comes out to be 5. So I have to place 5 orders. So the order quantity is obviously going to be the total demand for the year 10,000 divided by N star, which is 5. 10,000 over 5 will give you 2,000. So each order quantity will be 2,000 and you place 5 orders in the year. So once you find N star and you know the annual demand, going to Q star, the optimal order quantity or the EOQ quantity or the optimal lot size, different terms for the same thing, is relatively straightforward. You take the annual demand, you divide by N star. And it's more straightforward in this case to find N star because the products share the shipment. So N star is the same for all the products that you're going to order through this in such a situation. Right, because we are saying we can combine the shipments of these products, and so all the 2 or 3 products we order together like this, they'll have the same number of shipments, and N star is the number of shipments we'll get in the year. Okay, so to find N star is kind of like this EOQ formula. You have demand at the top, right, and you have the S, the ordering cost at the top, then you have it at the bottom, but it's kind of similar. And so you take the annual demand times the holding cost times C, okay, and I'm going to explain what these terms are. And then you're going to add it for the second product. So L is product 1, okay, and M is your second product, and C is your third product. You could call them 1, 2, 3, call it D1HC1 and D2HC2, D3HC3. The subscript doesn't matter, it's just however many products you have, that's how many terms you'll have at the top. Divide by 2 of S star. S star is this special ordering cost which is made up of a fixed ordering cost, which is irrespective of the number of products you order, and then each product has its own ordering cost. So imagine that S is something like your shipping cost. Whether you have one product in the shipment or two or three, doesn't matter. You have to pay for the full container to be shipped. But each product that you pick up, the 3PL charges you a pickup cost. So SL would be how much it costs to pick up product L. And if you don't have product L, you don't have any SL, right? Because you're not picking it up. So you split your fixed cost into two components. One is product specific. That'll be SL plus SM plus SH, each one term for each product. And then one is not product specific. It just applies to every shipment, which is the capital S here. So S is the fixed ordering cost. It does not vary with the number of products. That's this S right here. This one here. Okay. And the other SI variables reflect ordering costs that are due to each individual product. So and then if you have K products, you can generalize the formula. The sigma here at the top just means summation. So you sum all the D times H times C terms at the top, divide by 2 times S star square root, and then S star is the fixed cost per order, which does not depend on the products, and then each product has its product specific ordering cost as well. Okay. And then once you have calculated N star, optimal order count is given by the demand for each product, the annual demand divided by the N star. Okay. N star may be a fraction. You leave it as a fraction. Why? Because if you are going to place 4.5 orders per year, you're not going to place 4.5 orders. You either place 4 or 5. But what it means is some years you place 5, some years you place 4. So it averages out to 4.5. So you want to keep the 4.5. Okay, don't round it down to 4 or something like that. So you can follow this example on slides 14 and 15 to see how this formula works. This is also built into the SCM inventory workhorse Excel file. If you go to, this is the standard EOQ formula and the lot sizing, but if you go to lot sizing multiple products, it's built into here. So all this data for the first product, demand for second product, whatever you don't have, if you don't have a third product, just zero it out. And if you have a fourth product, then you have to extend these formulas and have D4 demand 4 here, right? But in any case, it's been set up to do 2 or 3 products. And so let's put in our data into this worksheet first, and then I'll also show you how to do it manually if you don't want to use this template I'm providing you. Okay, so we go to our question. Okay. Acquisition cost, the cost we pay the supplier is 90. That's the C. So I said I was going to explain the C. This is the cost we pay for the product we're buying to the supplier. That's the C. So CL is the cost, which is the supplier's price to us in a way. And if you have like taxes, duties, other expenses which are associated with buying each unit of the product, they will go into this C. So this is like the cost to us, whether all of that goes to the supplier or some of it goes to tariffs or whatever, that's the cost to us, C. Okay. So in the question, we have premium tires cost $90. If you go to your SCM workhorse, C1, this is for premium tires, you put in $90 right here. This already has the data from the question because when I made this sheet, I tested it with this question. So I think a lot of the data is already from the question we're doing. But anyway, under cost 1 for the first one, you put $90. Okay. Discount tires cost 50, so you can go back here. Under C2, you'll put 50. Okay. Then you need 10,000 premium and 14,000 discount. So go put in that data. This is a demand. So demand D1 is 10,000. And D2 demand of discount tires is 14,000. Now, not 140, 14,000. Make sure you enter the right demand matching the right cost. So the expensive tire has less demand and the cheaper tire has more demand. If you flip these two demand values or you flip the two cost values, then things will not line up and then you'll get an error. Your calculation will be wrong. So we got the demand, we got the cost. Inventory carrying cost is 20%. So that will go here, which is small h. Small h is always a percentage. You can put in 20. If you have capital H, that is small h times the C value, but we have the C value entered separately and small h as a percentage entered separately. Right, so we'll keep this as 20%, and it will multiply 20% by 90 to get the holding cost of 1 unit. Because each unit will, it costs us 20% of the value of that unit to hold it in inventory for 1 year. That's what small h is. Small h is how much money do you have to pay to hold 1 unit of something in inventory for 1 whole year. So 20% means it's going to cost 20% of the value of the item. So 20% of $90 or 20% of $50. So we put that in. And now we have the ordering cost. So fixed cost is $100 plus 50 per product. Okay. So we'll put $100 as the S. Okay. And then each product gets 50, which is the product specific S1 and S2. So total S star will be 200. There'll be 100 plus 50 plus 50. This white cell, the 200, is a formula. Don't try to change it manually. The green cells are your input cells, so just put in values in the green cells. We're going to zero out any value for C3, S3, D3 because we do not have a third product. If you did have 3 products, we'll put in the stats for the third product here. Okay. Now once you do that, sorry, I didn't mean to change that, it's 20%. Then you'll see that the optimal number of orders comes out to be here to be 28.28. That's your N star. And then you're going to divide the annual demand by N star to get the order quantity for premium tires. So if you observe, I take the annual demand 10,000 divided by N star 28.28. Same thing I do here. I take annual demand of 14,000 divided by 28.28. And I get the optimal lot size. Okay. Okay. Now this is trying to calculate how many days inventory stayed in our system on average. So once we receive the product, on average about 6 days later it's gone out of our system because we are ordering a pretty small order quantity. We are getting very frequent orders. Okay, but you don't have to worry about this for the homework for now. You just need these 2 values. So the optimal lot size for premium tires, product 1, is given right here. So let's take this and put it into our homework. 353.55. So 2 decimal places, that'll be 353.55. And then for discount tires, it is computed alongside the other calculation is right here. That's going to be 494.97. Now, let me show you quickly how to do this question without using the inventory workhorse. So we can just put in all the data. Okay, D1 is 10,000, D2 is 14,000, S was 100, S1 was 50, S2 was 50. So S star was going to be S plus S1 plus S2. That's the ordering cost. Then the holding cost is 20%. Okay, you have to enter 20% like this, or you put in 0.2, but then don't do a percentage. So just format the normal cell and put in 0.2 because 0.2 is 20%. Or if you format it as percentage, then you have to type in 20. Don't format it as a percentage and type in 0.2 because that's going to be 0.2% or 0.002. So 20%, or if it's not a formatted as a percentage, then you type in 0.2 because 0.2 is equal to 20%. Then what else do we have? So demand, we have the cost. So C1, $90. It costs us to get the premium tire, and the cheaper tires are $50 a piece. Okay, so how do we find N star? Well, the formula has a square root if you go to the slides, and we take demand times H times C, this term for every single product you have. So we take demand times H times C, make sure the first demand goes to this first cost, plus for the second product, do second product demand times H times C. Okay, and you divide this whole thing over 2S. So I'm going to add an additional bracket here to take this whole top part and divide by 2, also in brackets, 2 times S star, so 2 asterisk S star, and then put the whole thing in a square root, and we've got 28.28. Let me zoom in so you guys can see better. So you got N star of 28.28 by putting in this formula, which is coming from this slide in your lecture, in your lecture slides. So the optimal lot size for multiple product slide. Okay. So when N star is not sufficient, we need Q star for premium tires and Q star for discount tires. So this is going to be the annual demand for premium tires divided by N star. And this is just going to be annual demand for discount tires divided by N star. So let's verify our answers with the inventory workhorse. We got 353.55, which is what we got here. And then we got 494.975, almost 0.98. And 0.97 right here. 975, exactly the same number. Okay, so we're getting exactly the same numbers. So you could do it by yourself by putting in the formula. It's not that complicated. This is the formula for N star right here. Or you could just use the inventory workhorse file, to compute it. And the formula is given right here. And you also have a worked example in the slides. Okay, so that's it for the first couple of questions. Now we should move on to the remaining homework. We're going to do the Kung Fu Panda scenario, and then we're going to do the Ford event t-shirt scenario, inventory management questions. So for this question, we're given some data, and we have data on demand, and we have data on lead time. Okay, so you can see that demand is changing day by day. It's not constant. Lead time is changing day by day. So immediately we know it is the scenario in which demand is variable and lead time is variable. Next thing we notice is that inventory levels are checked once a week. So it is not continuous review. It's a periodic review inventory system. Okay, first thing we have to find statistics on demand and lead time. So we can use the average function of all of the data points to find the average demand. Then we can use the standard deviation SDDEV.S. This is a sample of data on the same values, and we get the standard deviation of demand. So this is called SD or sigma D in the formulas, and this is called small d, it's demand per day. It's not annual demand. Big D is annual demand in formulas. We do same thing for the lead time. We use the equals average function in Excel, select all these values, which are actually less than the values here. Now, if you do select empty cells in Excel, it does not affect your statistics. But if there's a 0 here, it will affect your statistics. So empty cell means not 0, nothing in it. So empty cells do not affect the average or the standard deviation, but we can just exclude them anyway. Just select the data, and that should be our average lead time. Similarly, we can find the standard deviation of the lead time for the 20 orders that we are given the data for, and there is a standard deviation, a non-zero standard deviation of lead time, which is called sigma L or SL in the formulas. We can see from the slides that when you have
variable demand, variable lead time, the standard deviation sigma p plus L that we need for the safety stock calculation for a periodic review system, which is what we have here, is given by this long formula. So you do P plus the average L times sigma D squared, which is SD that we written in Excel, because sigma is kind of hard to write. You have to insert symbol in Excel. So I just replace sigma by S when I write it out. And then we have a D squared, and then you have the lead time sigma L or SL squared. It says LT here. You can call it L or LT. That's the lead time standard deviation squared. So if we go to our Excel sheet, we have to find that the sigma of P plus L, okay, and to do that we do a square root, okay. We know that this whole thing is under a square root. Then you do P plus L. So we have not written out P plus L first. So let's do that first. Well, we have L here. We need P. P, I believe, is 7 days. Once in 7 days, inventory is checked. Okay, and we can just double check with the question. Once a week to check inventory levels. So every 7 days inventory is checked. So that is P. Okay. So we do square root of P plus L times standard deviation of demand squared plus, let's check the slides again to get it exactly right, the average demand squared and standard deviation of lead time squared. So then we'll take the demand squared times the standard deviation of lead time squared, and that gives us as sigma P plus L, standard deviation of demand over the P plus L interval. Once we have that, we multiply that by Z to get the safety stock. So Z we need based on the cycle service level, which is 98%. So we do equal norm.s.inv 0.98, convert probability to a z-score. Norm.s.dist will take a z-score, convert to a probability, and norm.s.inv is the reverse, give it a probability like 0.98, will give you a z-score. So that's 2.055. So then we have safety stock is simply the z-score times sigma P plus L, which is right here. Okay, we're going to need the average inventory level as well. So if we go to this slide, slide number 26, we have average inventory level is given to, this is a safety stock, just calculated that. So we have average demand times P over 2 plus the safety stock. Okay, so we take the average demand times P divided by 2 and add to that the safety stock, and that's our average inventory level. Okay, so we have to calculate a T as well, and the annual holding cost. Okay, to calculate annual holding cost, that's really easy once you have AIL. We need some other parameters. We need the holding cost H, which is 25%. We need the cost of each item, which is $2. So this is all given in the question. Box of noodles costs $2. That's C, the cost of an item. And holding cost is 25% of the item's value, so it's 25% of that. So annual holding cost will just be H times C. H times C gives you the annual holding cost of one box of noodles. But how many boxes of noodles are you actually holding? Well, we're actually holding average inventory level box of noodles. So we multiply by that, and that's our average annual inventory holding cost in dollars per year. We need to find the target level T. We can go quickly back to our formulas to find T. So T is equal to average demand times P plus L plus safety stock. So that's really easy. We take the average demand times P plus the lead time, just plugging and chugging the formula. That's D times P plus L. So D right here times P plus L plus the safety stock. So once you get safety stock, things become easy, right? So that's your T. Okay. So that's pretty much it for the Kung Fu Panda scenario. We're going to do a periodic review system, safety stock we calculated, target level T we calculated, average inventory level AIL we calculated, annual holding cost we calculated. Last question, if you're holding 2570 boxes in inventory, you have placed an order for 3000 boxes. So inventory at hand, 2570, inventory in pipeline, i.e. orders placed, 3000. That means my inventory position is going to be inventory on hand plus inventory that's already been ordered, that's on the way. That's my inventory position. And how much will I order? You'll order to take inventory position up to T. So the difference between T and the inventory position is how much to order. So order quantity will just be this number T, the target level, minus the inventory position. That's 1462.5 or 1463 to the nearest integer. Okay. And now that's it for the scenario. Now we do the Ford scenario. So we're selling some toy versions of a car. We have a demand distribution given here. And what's the optimal quantity to keep in stock? So I took the liberty of entering the question data here. So this is the probability distribution. I know I'm going to need cumulative probabilities. So what I did is I know that the probability of 100, okay, is 0.05. So what is the probability I'm going to be less than or equal to 100? That's simply 0.05. Okay. Okay. What is the probability I'm going to be less than or equal to 200? Well, that's the probability I can be 200 or lower. So that's these two probabilities added together. So if you add those two probabilities, you get 0.11 plus 0.05 or 0.16. Similarly, you can just drag the formula down. 0.34 plus 0.16 gives you 0.5. The probability you're going to be 300 or less in demand. Demand can be 300 or less is equal to 0.5. That's a cumulative probability, and it goes up all the way to 1. Now, to do any of this analysis, you need to find cost of excess and cost of shortage. So C is cost of excess, CS is cost of shortage. So think about it this way. If you have one extra t-shirt left at the end of the day, what is the cost of that? Well, you paid $40 for the t-shirt at the start of the day to bring it to, not the t-shirt, just the toy car. So you paid $40 for the toy car, whatever item we are selling. What are we selling? Ford Mustang toy cars, right? So it costs us $40 to buy the toy car from the supplier. And at the end of the day, when we have this one extra toy car left, when we return it to the supplier, he'll charge us a restocking fee and only pay us back $30. So we lost $10 by having this extra car. So my cost of excess per unit, this is for each extra car, is $10. And the cost of shortage, if I have one less car than I needed, well, if you had one less car than you need, then you sold one less car. So what is the loss of not selling a car? You sell for 75, you buy for 40, you make $35 profit on a car. You lost that profit because you didn't have that one car in stock. So the cost of a shortage is $35. So our critical ratio is CS, cost of shortage, divided by CS plus CE. So we do that, and our critical ratio is 0.777 or 0.778. And so we have to find the cumulative probability, which is 0.778, and read off the quantity here. Now there's no 0.778 here, so we go to the closest next highest probability. We don't round it down because we don't want, because usually the cost of shortage is higher than cost of excess. And so we lean towards having too much rather than too few. So if you lean towards having too much rather than too few, then you're going to round the ratio up, right? So usually, as a rule of thumb in this course, you can just round the ratio up. Although it, in some weird scenarios where cost of shortage is too small and cost of excess is a lot, it may make sense to round the ratio down in the cumulative probability table. But you're always going to round it up because we're going to go with a normal scenario where cost of shortage exceeds cost of excess. So in the normal scenario where cost of shortage is bigger than cost of excess, we round, and for this course, that's what we're going to assume. We round this up to the next highest value. So it's going to round up to 0.84 because there's no 0.778. It's between 0.5 and 0.84. So if you round to 0.84, you get quantity of 400. So we will order 400 toy Ford Mustangs and take the 400 to our stand to sell. Now, the second part of the same problem, is that we have exactly the same setup, except this is not our demand distribution. We have kind of estimated that our demand is going to have a normal distribution with a mean of 350 standard deviation of 100. So we're going to still use the same ratio because cost of excess, cost of shortage has not changed, and so our ratio has not changed, right? And so it's going to be the same ratio. Okay, but our demand distribution has changed, so we put that ratio not in this table but somewhere else. So that's going to be our z-score, and then we're going to use this. So we're going to do norm.inv, okay, our ratio, and then our mean is going to be 350, standard deviation is going to be 100. So that's 426.47. And let's check the rounding rules in the question. Round to 2 decimal places, so we'll just enter 426.47. Another way to do the same thing is that you use norm.s.inv. That S means it's standard, so you just give it the z-score. It doesn't need mean or standard deviation. It just needs a probability. So it uses a probability, which is 0.778. It converts the probability to a z-score of 0.7647. And then you can convert the z-score by multiplying the z-score by the standard deviation and adding in the mean, and you get to the same answer that you got with norm.inv. So norm.inv is the one-step way to get it, or if you want to first convert the probability to a z-score, you can do that with norm.s.inv and then convert the z-score using these back to the actual scale of the quantity we are concerned with. So that is it for this fourth scenario as well, and that ends this video. Hope it was helpful. If I went too fast, you can probably this controls to slow down or speed up the video. You can pause, you can slow down, you can rewatch. Do this in your own Excel so you get